kids, it's Mrs. Geiger here. So we're actually going to start a new unit, and that new unit is called Kinetics and Equilibrium. So the first thing we're going to talk about is this idea of kinetics. Kinetics is the part of chemistry that discusses how fast reactions occur, as well as how much energy it takes for reactions to occur. So the first thing we're going to talk about here is something called collision theory. You should know that this word collision means that the particles are going to be hitting into each other. All right, so collision is just a word in English that means that things collide or hit into each other. So collision theory says that particles must hit into each other or collide in order to react with each other. Remember, a reaction is a rearrangement of electrons. So in order for particles to change their electrons, they need to hit into each other. So it's not good enough for particles to collide. They must have what we call an effective collision. All right, so think about it this way. If these are going to represent atoms, and if we want the electrons in one atom to move to the other atom, let's say that we're simulating an ionic bond. If they bump into each other, that doesn't mean that we're necessarily going to have a chemical reaction. There's two criteria to have a chemical reaction. So we'll get to that in a second. Start to think about what would need to be true in order for the particles to rearrange their electrons. So we're going to see here an effective collision is one that results in a chemical reaction. All right. So there are two criteria for an effective collision. The particles need to have enough energy when they collide in order for the electrons to move. So I'm going to simulate that. If I have the atoms come together, they can change shape and bounce off of each other. But this model, the way that it works is if there's a chemical reaction, you can see that they light up. And they even squeak a little bit. So, what needs to be true in order for the particles to hit so that the chemical reaction occurs? Well, they need to have high enough temperature. How does temperature relate to particle motion? If you increase the temperature, how does the particle motion change? So you should be thinking, oh, well, it's the speed of the particles, right? So we can say that they have a high enough temperature. Remember that temperature is a measurement of the average kinetic energy. So they have to have sufficient or enough average kinetic energy, or you can say speed. Right? Temperature measures the how fast the particles are moving. So the particles, if they're going too slowly, they're not going to have enough energy. When they bounce off of each other, they'll just bounce off and they don't react. And this happens all the time. But if they do have enough energy, if they're going fast enough, they will be able to rearrange their electrons. And that rearrangement of electrons is a chemical change. Now there's something else that needs to be true. The way in which they hit into each other, which we're going to call the orientation. So many of you in your projects have looked at things that had different arrangements of particles or different arrangements of atoms within a molecule. So If a molecule is not oriented the right way and it collides, but there's no electrons available on that side, then it might not have a reaction. It needs to be oriented in the right way where the reaction can occur. And remember, we go back to this form and function idea all the time. All right. So what could we do to speed up a chemical reaction? What could we do to make that reaction go faster? Think about what you could do, what things you could change about substances. And think back to when we did dissolving. What could you do that would change how fast, or change this to be able to happen faster? So we're going to say the rate of the reaction is a measurement of how fast products are formed in a reaction. It's kind of self-explanatory. The unit for rate of reaction is usually change in molarity over change in time, or it could be the change in mass over a change in time, depending on if you have an aqueous solution, you'd be measuring molarity. If you were creating a solid, then it would be the mass, or if a gas was being released or created, it would you could even do if it was a gas, the change in pressure over the change in time. But those units never really come up very often, so you don't worry too much about them. All right, so make predictions. What do you think are some of the factors that could increase how fast a reaction happens? So go ahead and pause the video and make those predictions. Okay, we're back. So I'm just going to let you guys know what they are. So the number one thing that you should know is temperature. This is why when you leave the milk out, it goes bad faster. So if the particles are moving faster, the reaction rate will go faster because the particles will collide more often and they will collide with more speed. So more particles will have enough energy in order to react. Something else you could do. That's right. If it's a gas, you could increase the pressure. You guessed it. If it's a solid, you could increase the surface area. There are two more factors here that we're going to talk about that you might not have. Oh, I'm sorry. I forgot the fourth one. If it's a solution, how could you get more collisions? That's right. You could increase the concentration. Right, so there's two more that we're going to talk about that you might not have thought about. Number 5 is going to be called nature of the reactants. And so what that means is that if the particles start out more spread out, they are more likely to react faster. So if you have an ionic solid and you dissolve it in water, it will react faster than if you left it in a solid. So major idea here is that the more spread out particles are, the faster they will react. So if you can create a situation where the particles get more spread out, that makes the reaction happen faster. And that's basically what we're doing with surface area, right? Surface area here only applies to solids, and concentration only applies to aqueous solutions. But if you think about how surface area is, when you crush something up, you're really spreading the particles out more. Same idea for nature of reactants. And there's one last one that is unique to this unit that we've never talked about before, and that is called a catalyst. A catalyst is a substance that you add to a reaction to make it go faster, but it's not actually involved in the reaction. So, the best analogy I have for you for a catalyst would be a T-ball. Right? You're all familiar with baseball and the idea of T-ball. So, if I had my two particles and they were just bouncing around, they might not hit into each other and then eventually collide. But if I had them where one of these particles was introduced to a substance that allowed it to stay here, like it was a T on a T-ball, this particle coming in has an easier time having an effective collision because the catalyst is a helper to the reaction, but it's not used up in the reaction. So a catalyst is a substance that specifically increases the rate of the reaction, but it's a spectator. It's not actually involved in the reaction itself. All right. So moving on, the next thing we're going to talk about is a term called enthalpy. Enthalpy is also known as the heat of reaction. So enthalpy is also called the heat of the reaction. That's not really a definition, but we say that the heat of the reaction is the amount of energy absorbed or released in a chemical reaction. And another way to think of this is the net energy of a reaction. RXN is the abbreviation for a reaction, in case you didn't know. So I'm just kind of ran out of space there, so I use the abbreviation. So when I say net, I mean the overall reaction. We all know that when particles get closer together, energy is released, and when particles get further apart, energy is absorbed. So usually in a chemical reaction, particles need to, in the reactants, break their bonds and form new bonds. That means that there's an overall net energy to the reaction. So we have this formula here that says that the change in enthalpy, oh, I forgot to mention that enthalpy has the symbol H, and that is not because of it standing for heat of the reaction. Remember, heat is Q. H is actually because the person who coined this was named Hess, and so he gave it an H for Hess, but it's the heat of the reaction. So you'll see that here on table I. So right now, pause the video and go find your reference tables and take a look at table I. All right, so we're back. So you'll see that when I say here the change in enthalpy, the overall heat of the reaction is the enthalpy of the products minus the enthalpy of the reactants. Now, it's different than heat, but we're just talking here about the potential energy that's stored in the bonds. So the potential energy that's stored in the bonds of the products would be like the final energy minus the amount of energy that was stored in the reactants, which is like the initial. So you should know that delta always means that there's a difference, and so it's usually final minus initial. Here we're going to say specifically products minus reactants. So here I have my table I, and what table I shows us is the overall energy that is either absorbed or released during a reaction. If overall the reaction absorbs energy, there's a net gain of energy. The products have more energy than the reactant started out with. We have absorbed energy. There's a word for this. What's the word for when energy enters the system? You got it. You know it. You've known this since September that's, oh, sugar. Why does this keep jumping? You've known that since September that's called endothermic. All right. Now, if there's a negative value, that means that there's a net release of energy. The reactants had more energy than the products end up with. Overall, there's a release of energy. There's a net loss to the environment. So you all know that when energy exits the system, that's called, you got it, exothermic. All right, so Table I will tell you if a reaction is exothermic and gives off heat, or if a reaction is endothermic and absorbs heat. So I just wanted to take a look at Table I. Table I here is actually broken up into sections. So I just wanted to show you what those sections were. This first section here, you'll notice that these reactions all have something in common. It's this to here. They all have what is known as a hydrocarbon molecule, something that is covalently bonded that's made out of carbon and hydrogen. And some of them have oxygens in them. Those are called substituted hydrocarbons. Don't worry too much about that. But you should notice that it's a carbon-based substance, and it's reacting with oxygen to produce carbon dioxide and water. So that should look familiar to you. So especially this one, C6H12O6 plus 6O2, CO2H2O, that's respiration. But what you should know is that these are all combustion reactions. Combustion. Combustion just means burning. So all of these reactions are burning reactions. Now take a look at their enthalpies. What do you notice about the values of their enthalpies? That's right. All of these reactions have a negative enthalpy because they're burning of something. And we usually burn things to get heat, to give off the chemical energy, change that potential energy that's stored within the bonds into heat energy. So those are all combustion reactions. Now let's take a look at our next section. Our next section of reactions goes from here down to here. You should recognize that this is one of the four major types of reactions. These are all synthesis reactions. All right. So when you take a look at a synthesis reaction, you should notice, like I'm going to focus on this one of making nitrogen monoxide. This reaction here, you'll notice, is endothermic. But what that means is that the decomposition, the reverse of that reaction, is exothermic. So this section you should recognize are all written as synthesis. But what you should know is that when you have the reverse of a synthesis and you do a decomposition, if the forward reaction is endothermic, the reverse will be exothermic and will give off the same amount of heat that the forward reaction absorbed. Do you remember when we had the copper sulfate pentahydrate and I had you touch it? And the forward reaction was endothermic, it broke the bond, and then I put the water back in and the water smashed into the copper sulfate and made a new bond, and you felt the heat? That is that same example. That was a preview of this, that as if you have the forward reaction is endothermic, the reverse is exo, and vice versa. This next section here, we have, I'll do this one in red. This next section here, you should notice that there's something in common with all of these reactions. And that is that these reactions all have water above the yield sign. So that means that they're dissolving, right? We have solids on this side, and then we have aqueous ions on this side. So these are all the dissociation of those ions. So this is all dissolving, these ones. I'm just going to write dissolve. So I'm kind of running out of room here. So those reactions are all dissolving. So they're actually physical changes, not chemical changes. And you'll notice that some of them are endothermic and some of them are exothermic. Actually, dissolving of sodium hydroxide is super exothermic. And so if I ever make a solution of sodium hydroxide, I have to make it and then let it sit because it gets really hot and it's kind of dangerous to use until it gets down to room temperature. And sometimes you have to add a little bit more water because it's so hot, the water will actually start to evaporate. All right, and then our last reaction here, you should recognize that this H plus OH minus yields H2O. That is neutralization. All right, it's the net ionic for the neutralization reaction. All right, two things I just wanted to point out at the bottom. It says that the H values are based on molar quantities represented in the equations. We'll get to that. We're going to do a little stoichiometry because what that's saying is that this amount is based on the lowest ratio possible, the balanced reaction. But what I have here in this red box is a minus sign indicates an exothermic reaction, which I don't like that they said minus sign. I want them to say a negative sign, but that's okay. So what that is to tell you that on this, that if you forget ever that the minus represents an exothermic reaction, it's right there on the table for you. All right. All right, so the next thing we're going to talk about is conservation of energy here. So in a chemical reaction, nothing is lost. Mass, blank, and charge are conserved. You got it, that's energy. So, if a reaction is endothermic, that means that energy is being absorbed. If a reaction is exothermic, that means that energy is being released. So, when we put the energy term, when we put the amount of energy in a chemical reaction, we can do this and also have the reaction and have the heat term right in the chemical reaction. And if something is endothermic, it is absorbing energy. So, we're going to put that energy as a reactant. If the reaction is exothermic and overall it gives off energy, energy is written as a product. All right, so it's like you can think of the yield sign as kind of like the door to the reaction. If energy is entering, it's going to be a reactant. If energy is exiting, it's going to be a product. All right, so let's do two examples of this. I'm going to choose an exothermic and an endothermic reaction from, here's my table I, right? So I grabbed this reaction, which is the synthesis of C2H6, which has the name ethane. All right, so is this reaction endothermic or exothermic? You got it, it's exothermic. Good. So I'm going to go ahead and rewrite this reaction, but I'm going to put that 84.0, and what is the unit? You're right, it's kilojoules. We see that right up here, right? So this is all in kilojoules. So I'm going to add that as another product. So that means that I'm going to write this reaction as 2 carbons, solid, plus 3H2 gas yields C2H6 gas plus 84.0 kilojoules. Oopsie, I'm moving my picture in picture. I'll move myself up here. Kilojoules. So now remember, in a chemical reaction, you should never have minus signs. We just kind of rearrange it so everything is plus because we want to show how things are colliding with each other. They're adding. So instead of having a minus 84 as a reactant, we're kind of going to move it to the product side, and we're always going to have plus, but show that it's being given off. It's being released. It's one of the products of the reaction is this 84.0 kilojoules of heat. All right. All right. I'm going to just go ahead and choose the reaction right above that to do my example of my exothermic reaction. But there's another reason. moving the table instead of my selector there. Okay. The reason I'm going to choose this reaction also is that this is one of the most important reactions that exists, and this is called the Haber process or the Haber process, depending on how bad your accent is. I always say it's the Haber, but a lot of people say it's Haber process. And this is how we create fertilizer, and this is why we're able to not have food shortages. So the Haber process, you're actually going to watch another video on this, and we'll talk about why this is so important. But that's a really, really important reaction, and the Regents asks about it all the time because it's so important. So let's use this as our, oh, I'm sorry, that's also exothermic. Let's pick a different one for endothermic. Let's choose this one right below. There's the one right below here. I'm going to choose a different one. I'm going to go ahead and choose this KNO3 one. I changed my mind. Okay, so this is endothermic. So instead of the energy being a product, now it's going to be another reactant. So the way that we're going to write this looks like this. We're going to say KNO3 solid plus 34.89 kilojoules yields, and I'm going to put my H2O above my yield symbol. The reason that we put it there is because it's kind of a reactant, but we don't want to have to deal with balancing it. And since in the products it's contained in the aqueous, we put it above the yield symbol. All right. So that's just why that exists there. This is going to be K plus aqueous plus NO3 minus aqueous. All right. So that is showing how an exothermic thermic reaction has the heat as a product, and an endothermic reaction has the heat as a reactant. Cool. All right, kids. Thank you.